So let's take a look at a problem that deals with a time-varying current while we're still in the time domain. Most of the time when we have time-varying fields, we'll jump into the frequency domain, as those problems are usually easier to solve in the frequency domain and we can gain more insight there. But some problems like this call for a time domain solution to a time domain problem using an alternating current. So what do we have here? We have a question that asks us to develop an expression for the magnetic vector potential, or in other words, vector potential, at the origin due to a circular current. I of t is given, where I naught is real, located at, it gives you the coordinates there. And if you're interested, I would assume at this point you would know how to draw such geometries from a vector calculus course or an introductory course in vector algebra. And it gives you a vector potential equation, which is basically a very simple integral, and it asks you to show all the steps in the derivation. So basically, you know, what's the field vector, what's the source vector, what's the difference, what's the magnitude of that, what's the differential element, and what is the time retarded current, which is that last I inside the square brackets. So why don't we start with the field vector. Now the field vector, as you may know, is the point from the origin to the point, or to a point of interest. In this case, the point of interest is the origin. So that vector would go from the origin to the origin, which would be a vector of length 0. What about the source vector? Now the source vector is a vector that goes from the origin to some point on the source. Now what's the source? The source is the thing that's creating the field. So in this case, the source vector should go from the origin to somewhere on this loop. Now, you can argue that there are probably an infinite number, well, definitely are an infinite number of different paths that you can take to get from the origin to the loop, but we want to take the simplest or the shortest path, which is simply going along, let's say, that little line I've drawn there for r prime here, this orange, sorry, in this one it's pink. This pink goes to the orange from the green. So this vector here is going to be our source vector. Now the source vector is, well, we're going to be in cylindrical coordinates here since it's a loop, and in the cylindrical system the loops are probably the easiest to solve, or spherical really, but it breaks down to a problem of cylindrical really. But now the question is, what is the magnitude of this vector? The magnitude of this vector is going to be the same as the radius of this loop, which is simply a. So it's a rho. Now r minus r prime, which is really an intermediate result, is going to be 0 minus a in the a rho direction, and this will be minus a rho. Now the magnitude of that, which is used, you can see directly in that equation above for the vector potential, is simply going to be the square root of the sum of the squares of every component. That's quite the mouthful, but really all you're doing is you're taking every component in the vector r minus r prime, you're squaring it, adding all the results of them together, and then taking the square root. There's only one component, so we get lucky in this case, so it's minus a squared under the root, which is simply a. Simple enough. Moving on, what do we have? We have dl, so the differential line element, or the differential element dl, as you can see it's drawn in light green on the actual diagram here. And basically the differential element is saying we have this loop, this orange loop, this finitely long orange loop, and what I want to do is I want to find an infinitesimal current element. Now infinitesimal is just a fancy way of saying very small. So I want to find a very small element, little chunk, imagine, of this loop, that if I were to take a bunch of those little chunks and I added them all together, I would end up with the big loop. So if you imagine like Lego or something like that, or imagine anything that you have, you cut it up into really little pieces and then you add it all together again and you get the same thing at the end. So it's a really small piece of that loop that I want to be able to define using dl. So how do I define, or how do I describe a filamentary loop sitting in the xy plane using a mathematical expression? Well, I take rho, I take d phi prime, Now I'm taking prime because we're dealing with the source, and whenever we deal with things that have to do with the source, we prime them. And you notice we primed, we have r prime for the source vector. Now we have dl prime for the source differential element. Now I have d phi prime for the source differential, well, defining the source differential element there. And now this thing has a direction, because if you look, this obviously, I mean, I'm not just going to add these pieces in any random direction. I have to add them in a loop. And if I have to add them in a loop, then this thing must have a direction. And so this direction is going to be a phi prime. Now, in this case, this is for a general filamentary loop. In our case, we actually have a given and a non-generic radius, which is a. So I'm going to call this a d phi prime, a phi prime. So this is how I describe my loop in terms of differential elements. So now the last thing left for us to do in this little sort of pre-problem, or the setup I should call it, is to find the time-retarded current. Now, the time-retarded current is this little I with the square brackets around it, so I'm going to call it the time-retarded current. Now, there's nothing wrong with the current itself. All this means is that whatever effect or whatever change that might happen at the actual current or at the actual loop will take some time to have an effect at some other point in space. So if you imagine, it takes time for the wave to travel from the actual filament to the origin. Now, if it takes time to get from the filament to the origin, then I have to consider that effect, like what happens in between. There's a delay. What is that delay? How much is that delay? How do I find that? So basically what I do in a time-retarded expression, or a expression taking into account time retardation, I simply replace every t with a t prime, and I say that t prime is equal to t minus r over u, and I say that r is going to be simply equal to r minus r prime magnitude, so that was useful again, and u is going to be the speed of propagation, and if you know anything about electromagnetic waves, you know that they travel at the speed of light most of the time. R we found was a. So I can say that t prime is going to be t minus a over c. Simple enough. Now all I have to do is replace every t that I see in I with t prime, and then I can call that I with square brackets and say that is the time retarded current, or the current taking into account time retardation effects, whichever way you want to call it, whichever way is easier for you to imagine. So I'm going to factor out the omega here simply for the sake of, well, not really factoring anything out, but I'm just going to factor, or I'm going to use square brackets there. I'm not going to expand the omega in, I guess is what I wanted to say, because that'll probably overcomplicate things. So for now we have this thing. So our setup is great, and I always stress the setup. Once your setup is there, getting from the setup to the final answer is really simple, and it's very difficult to go wrong if you've gotten this far. So at this point, really all we have to do is we throw everything into our integral equation, and we hope for the best, and let's pray for a relatively simple integral, such that we're not sitting here integrating for the next half an hour, and we can move on to something more important and productive. So I have this expression, and if you're familiar with this expression, if you're not familiar, I guess you can just scroll up and you can see where it's from. It's actually given in the question, and if you're familiar with line integrals, you know that line integrals will only integrate over a single variable. Now, what do I mean? You integrate over double variables, so two-dimensional integrals, when you have surfaces or areas, and then three-dimensional when you have a volume. And so in this case, we only have a line integral, so we have the simplest type of integral that we possibly could have gotten. Now, if that's true or not for the actual arithmetic or the mathematics behind it is a completely different story. So what I'm going to do is I'm going to plug everything in first. We'll take a look at what it looks like, and then we'll start simplifying stuff. I guess we can talk about as well the limits of integration, because that's always a key part. If you go up here, if we go up here and we take a look at a DL. DL is what we're going to be integrating here. So this is the thing that's going to be being integrated. So let's this is going to be, we're going to integrate this thing. If I'm integrating this thing, then I clearly see that there's only one variable to integrate. What's the variable to integrate? Phi. Of course, phi is the only thing that's changing. The radius of the loop isn't changing. The height of the loop isn't changing. Only that angular component of the thing is changing, so we're going around the loop in a circle. Therefore, d phi is the only thing that's changing. Now the question is, what is that changing? What values is that thing going to change between? If you look at the way that the cylindrical coordinate system is defined, it changes between 0 and 2 pi. So I'm going to say that phi prime equals 0 to 2 pi. So these are our limits of integration now. So that's relatively simple enough. Inside I have mu cosine, I naught cos phi prime. Cos, well, I guess I can prime that in there as well. Cos omega t minus a over c, and this will be over 4 pi r minus r prime. Remember, it was a. I have a d phi prime a. Well, sorry, a phi was here, right? And sorry, was that given? And was that? No, sorry. A phi is not on this. A phi is on this. A phi prime is here. I apologize. So the current doesn't have a direction. The current kind of just flows, but the thing that has the direction is the differential. So that's a vector. The current is not a vector itself. And so now we have this integral to solve. We can take out whatever is constant, whatever is not dependent on phi prime. So I have mu I naught cos omega t minus a over c. A's cancel. That's convenient. So it's simplifying something at least. Over 4 pi. And I have phi prime equals 0 to 2 pi. And here I have cos phi prime d phi prime a phi prime. Now, I know there's somebody watching this right now and they're jumping up and down saying, oh my god, this integral is so easy, you just solve it, you literally just, integral of cosine, plug in 0 to 2 pi and you're done. I wish it were that easy, because it's actually not. So, if you were to do that, by all means you could do that, and you would end up with a result that says 0. But we know that the result is not 0. Well, chances are the result is not 0. But can you confirm that in any way? Of course you can. If you think about the way that cylindrical coordinates define the unit vectors, you will stumble upon the fact that a phi is described as minus sine phi ax plus cos phi ay. Now what does this mean? This means I can't directly integrate a phi across anything like that. I have a dependence on this thing. I can't just go ahead and integrate it directly and do whatever, because you'll find certain things start to happen when this sort of decomposition takes place. So let's plug these actual components into the integral, and then we can see what we get, and then we can start seeing what cancels out and what doesn't and what becomes what. So I still have this term outside, this time varying term, which is really independent of anything going on inside. And I'll have, this is phi prime equals 0 to 2 pi. And then I'll have that cos phi, remember, decomposes into, well, I don't need to write those there. I can write that here at least. So I'll write cos phi prime, and this will be minus sine phi prime ax plus cos phi prime ay. And this d phi stays there, prime, and now I no longer have that a phi there. Right? And so now this is the thing that I need to integrate. And so now if I go through and I actually integrate this entire thing there, I will end up with, well, we can go and expand it, I guess, first before we jump ahead to the integral. So let's go and take it one step further, just so everyone's on the same page. And then we'll integrate after that. So this is going to be 0 to 2 pi. And this is going to be minus cos phi sine phi prime ax d phi prime. Sorry, that's not a unit vector, that's prime. Plus, let's break it into two different terms. It's easier, well, at least for me. I find it always easier to decompose things into as many terms as possible when integrating. And really it just helps to keep things in perspective and see what's going on. So if you actually carry out these integrals and substitute things in, you'll find that this thing actually ends up giving you 0 result, and that the second integral can actually be expressed in the following way. So let's go ahead and I'll write mu naught I0 or I naught cos omega t minus a over c over 4 pi, and that thing on the inside turns into 1/2 2 pi plus sine 2 times 2 pi. Well, I think instead of writing all of that, let's just keep it simple. The whole thing, and I mean, you might think this is awfully anticlimactic after all that, really just turns into pi. So these pi's cancel, and what I'm left with is a equals mu I0 cos omega t minus a over c in the ay direction all over 4. So this is our vector potential. And the reason I'm trying to jump through all that, I think it's unnecessary steps really, and it'll just add a whole bunch to the length of this video. We still have a couple of more things to talk about before we get to the end. And I think that, it's really just an integration, relatively simple integration. I think this one, you can probably find it anywhere. I think you should be able to do it off the top of your head at this point, but, I mean, if not, you should be definitely practicing. So the second part of this question asks, well, it wasn't listed above actually. It says, ignore the scalar potential, and find E at the origin. So if you recall, in general, E in the time varying sense is minus the gradient of V minus partial A over partial T. So this is the time varying modification of E equals minus the gradient of V, which is a very basic and fundamental expression for the electric field in field theory, or the basics of field theory. So it tells us to ignore this, so that's convenient. We don't need to know that potential. So really all I need to do is I need to find minus the partial derivative of A with respect to time. And so this is going to be minus partial over time mu I naught cos, well, let's do it this way, because when you're taking derivatives, you really have to consider things by parts, or the chain rule, sorry, I'm thinking in terms of integrals. So when I do derivatives of functions that are within functions, such as the trig functions or exponentials, I usually like to expand things and look at each term individually. So when I take the derivative of the inside, as the chain rule asks us to, I can see very clearly that only one term depends on time. Again, just keeping problems as simple as possible, not making things overly complicated to like save time or cut corners. Really, I'll take the extra time, and I would highly recommend taking the extra time, but doing it like, safe and sound, slow and steady, so to speak. So why don't we factor out things that don't depend on time again? So that's mu I naught over 4, and this is partial over time. And here I'll have cos omega t minus omega a over c in the ay direction. And the derivative of the inside of this cos function is simply going to be omega, because this term is constant, and the derivative of this will be simply omega. So I'm going to multiply that with the derivative of the whole entire cos function. And so the derivative of, well, why don't we just write this out here first, times omega, and now the derivative of the cos whatever inside is going to be sine, well, minus sine omega t minus omega a over c in the ay direction. Now you'll notice these two negatives will really cancel one another, and we'll be left with omega mu I naught over 4 sine omega t minus omega a over c. And you can simplify that back to the way we had it before, but I'm just going to leave it like that because it really doesn't make much of a difference at this point. So this is, sorry, this is not a, this is e. This is e at the origin. So, in this case, what did we do? We were given a problem with a current filament at, well, placed about the origin, and it asks us to find, it gave us a time varying current. It asks us to find all these vectors to basically set up the problem. And this is the approach I think should be taken for every problem that is given in this way. Whether it's asked or not, step-by-step solving problems really, it prevents silly mistakes if you break down the entire problem the way we did, where we find the field vector, source vector, all this kind of stuff. And to this day, I have solved probably over 100, several hundreds of problems like this, and I still continue to solve them this way every time, simply to prevent silly mistakes. I mean, especially in high pressure situations such as midterms or final exams, it's really easy to make mistakes, so it's better to be safe than sorry. So what did we do? We found the field vector, source vector, difference, magnitude, differential element, put it all together, found the time retarded current, which again was simply taking into account the difference in time that it, or well, the effect difference. How long does it take for the effect from the actual source to be seen at the point of interest, in this case the origin. Threw it all in the integral, solved the integral. Remember, we had to decompose that into different components because there are certain parts of the a phi vector that actually depend on phi itself. So my recommendation would be, whenever you see a vector that is not uniquely defined, in other words, any vector that is not ax, ay, az, I would highly recommend decomposing that vector into its components and then actually solving it. There are certain cases, for example, radial vectors, such as AR, the vector in the spherical coordinate system, or a rho in the cylindrical coordinate system. Those ones usually don't need to be decomposed unless you're integrating with an angle. So I guess I should say, whenever you're integrating with an angle, in this case we're integrating over phi, it is probably the best idea to decompose the actual vector, because certain parts of that vector might depend on the angle. If you're integrating over a radial component or like a z component, like in cylindrical coordinates, then you're probably fine. So if the integral is dr, if it's d rho, if it's dz, you're probably fine. But if you're integrating over an angle, things can get a little tricky because you oftentimes forget which vector is defined in terms of which component. So once we made that decomposition, we plugged everything back into the integral, gave you a few spoilers, and that vector goes to 0 and that thing turns into pi. If you actually go through and solve it, I assure you it will be. I'm missing a prime here. I apologize for that. There should be a prime there. And then the second part of the question said, ignoring the scalar potential, find the electric field at the origin. This was our modified electric field for the time varying case. We ignored the scalar potential V as it told us to, and we simply took the time derivative of the vector potential to find the electric field at the origin. So if there are any questions about this video, please leave them in the comments below, and I'll be happy to clarify. Other than that, I want to thank you guys for watching. I hope you found this video helpful. Look forward to more videos in the future, and if you haven't already, hit that subscribe button so you get notifications as soon as videos are posted. Have a good one.